Okay, so now you're going to notice that in the next part, I have an ln written. ln is natural log. Again, you guys got to kind of put your minds back into the Math 3 class that you guys took. That's when we talked about logarithms and natural logarithms and things like that. I know you're probably sitting here thinking, like, where are these logs coming from? Where are these natural logs coming from? It's just the idea that when we have a scatter plot that's not linear, we're trying to force it to be linear. So in this case, since it was exponential, the inverse of an exponential is a logarithm. And when we did the logarithm of those response variables, it made it straight. It made it a line. But guess what? A logarithm and a natural logarithm are the same thing. So it really actually doesn't matter if you do a logarithm of the responses or if you did a natural logarithm of responses. Really, it's just a different button on the calculator. So, like if you look at this chart up here, we took the log of all that. Instead, what if I took the natural log? We abbreviate it as ln. Again, it's just a different button on the calculator. I want to show you that it does the same exact thing. Now, the process, the values might look a little bit different, but it does literally the exact same thing. So it says draw the natural log scatter plot here. Well, I'm going to go back to my calculator. And if you guys remember, I have in here, I'm going to scroll way over. List 1 is the explanatory, which is the course number. This is the original response, which is the amount of M&Ms remaining. Well, for now, I'm just going to delete out list 3. I don't need to use that. I'm going to delete out list 4. I'm not going to use that right now anymore either. What I'm going to do is instead of taking the logarithm of list 2, the remaining M&Ms, I'm going to take the natural log. Again, it's still a logarithm. It's just a different base logarithm ultimately. So instead of hitting log, I'm going to hit natural log. And if I hit natural log of list 2, it's taking the natural log of all of these values. Okay? So here we go. Again, I'm going to look at the scatter plot. So I'm going to look at the scatter plot. It's already set for list 1, list 3, so that's the course with the natural log of the remaining. I'll hit zoom 9 to see that. And what do you know? The graph looks exactly the same as if I did a logarithm. So, and I'm going to come on over here, and I could pretty much just do that. Well, maybe I'm not going to do that. I was going to try and be cool with my technology, but I'll just redraw the same picture. The idea here is I was going to copy and paste it down here. And the reason I can do that is because it's literally the exact same graph. I took the course, which was in list 1. And instead of taking the log, though, I took the natural log of list 2, which I put into list 3, or in other words, I took the natural log of the remaining. Now, the actual values are different. If you compared the values of the logarithm remaining to the natural log remaining, the values actually are different. But the relationship between them is exactly the same. Like, it's literally the same graph. I maybe made that a little bit too high, but it's draw the picture is the exact same. I'm not even going to bother showing you the residual plot because, again, it would look exactly the same. But I don't want you to get confused. A natural log is still different than a log. They're both logarithms, but they're different base logarithms. So I can't just copy down this least squares regression line. It's not going to be the same. So let's run the linear regression to see what the new line would look like. Okay. If I come over here, again, to run linear regression, you hit stat, scroll over to calc, it's option 8, linear regression, a plus bx. We're going to still do it on list 1, comma, list 3, which is the natural log version, okay? So we're going to run it, and notice, sure enough, it's different. The y-intercept is different. Before it was 1.76. Before the slope was negative 0.296. They're different y-intercept and different slope. That's because the natural log and the log are different bases. They give different values. It does produce the same looking graph, but the actual equations are different. So when I come over here and I write it down, I could also, again, write it as y hat equals the y-intercept of 4.059 minus 0.681x. But this is if it was actually a line, and if I took just the the actual list 2, which had the remaining number of M&Ms. But remember, I didn't just do the remaining, I did the natural log of the remaining. So you've got to add the natural log into the equation. Another thing that I ended up putting in here was let's find what the R is, okay, or the correlation. The correlation ends up being negative 0.99, and I meant to do that up here and I didn't, but it ends up being the same because these are the same picture. But let's take a look at why natural log or logarithm is better. Again, I'll add this in here. This one would have also been negative 0.99 because it hits it just as good. But if you look back at the original line, when we tried to find a least squares regression line on the curved pattern, we had a pretty decent correlation. We had a negative 0.9 correlation, but we saw that it was clearly curved between the residual plot and the regular one. And while negative 0.9 looks great, in the end, it's not going to be a great predictor if you wanted to go beyond a little bit of this, you know. We want to predict it as best as we can. Well, as soon as we put in the log or the natural log, the correlation became so much stronger. I mean, you're practically at negative 1, which is as best as you can get, either a negative 1 or a positive 1. So this just shows that taking the logarithm or the natural log is going to be so much more fitting to the line. Okay? So again, we can use this new natural log version of the line to predict how many M&Ms are left after the second course. So similar to what we did above, we're going to use the formula, the natural log of y hat equals 4.059 minus 0.681x. Except instead of x, we're going to plug in the course. We're wanting to predict it after 2 courses. So the natural log of y hat equals 4.059. If you multiply it out, it's negative 1.362. So again, it looks like they're different values, but let's just keep going and see what happens. The natural log of y hat equals, if you subtract those, you get 2.688. And similar to up here, we have to get y by itself. Well, the base of a logarithm is base 10. Does anybody know what the base of a natural log is? If you forgot, it's a base e. E is a special number that we use in math. So I like to kind of circle this and go around, and so what I'm basically saying is y hat, the value we're looking for, is equal to the base of that type of log, e, to the 2.688 power. Since the base of a log is 10, we did 10 to that. Since the base of a natural log is e, we're doing e to that power. So we do have e on our calculator. If I go over here, e is found above the natural log button. It says e to the x here. So what I'm going to do is I'm going to go second e to the x. So it pops up the e for me. And I'm going to do 2.688. So that's the predicted number of M&Ms after the second course. And if you see, it's the exact same number we did if we did a logarithm of the exponentials. So our y hat is 14.7. So what I'm trying to show you guys in these predictions is it doesn't matter if you take the logarithm or the natural log. The idea is they're both a logarithm, they're both inverses of an exponential. So if you want to try to get an exponential to be more straight, either take the logarithm or take the natural log. It doesn't matter which one. Just make sure that you write the equation appropriately, like if you did a natural log versus if you did a log. Okay? Now the only other thing that you're going to be asked to do with this is how would you find a residual, which is, remember, the amount of error. Well, this is what was predicted. What we need to do is look at what the actual is. So I'll just remind you, the actual, you just got to look up at the chart, the actual amount was 13 after the second course. We got 14.7. Think back to that chapter that we did this on. To find a residual, remember we're in an AP class. So I taught you to do the actual minus the predicted. Well, we just found the actual. The actual was 13. This one is the predicted. So we take the actual of 13 minus the predicted of 14.7. So we say that our regression line Did it over or under predict? It over predicted by 1.7. Remember, if it's negative, it over predicted. If it's positive, it under predicted. So you will be asked to predict how many. You will be asked for residual, and you're going to have to go through the process of using either a natural log or a logarithm. Just pay attention to the problem. Does the problem ask you to use a log? Does it ask you to use a natural log? Either way, you're going to get the same answer. It's just a matter of knowing which one you need to use for your formula. So that ends up being pretty much what you're going to be expecting for achieving linearity. The reason we say achieving linearity is because we're trying to make it straight. We make it straight by using a logarithm. And so that's kind of the process that we look at. So what I have here is another example using an exponential model to find the line of best fit. So whenever you use a log or a natural log, we call it an exponential model. So it's just another example for you guys to try. I'll go ahead and make a video, one more, which talks about the answers to this, but I want you to give it a shot first. Try to use the ideas that we did in this video and the last to try to answer this question, and then go back and watch the last video to get the answer to this page. All right, so good luck.